Thank you. Hello, everyone. My name is Matthew Dooley. I'm a cyber researcher with the Johns Hopkins Applied Physics Lab.
And my name's Anthony Talamontes. I'm a manager. I manage cyber operations at the lab. There it goes. So, agenda, we're going to go do some background real quick. I'm going to talk a little bit about some of the data analysis challenges that we have had. Matt's going to go through a use case. I'm going to go through a use case, and at the very end, we'll talk about how do we apply. So just a little background. We are not the university or the medical center. We are a university-affiliated research center. Our sponsors include DoD, NASA. If you guys remember when that spacecraft flew into that asteroid and changed its trajectory, that was us. Like, we do cool stuff like that, which is kind of cool to say you work for a company that, you know, flies spacecraft into asteroids. 9,000 staff, $2.3 billion revenue. For a research lab, that's fairly big. We're one of the bigger DoD research labs. This is our campus in Laurel, Maryland. So I just want to do a little bit of, have a little discussion based on some of our past cyber attacks. In 2009 was kind of that pivotal big attack that the lab had. An APT targeted the lab. There was a lot of data that was exfiltrated. You know, we made the Baltimore Sun, you know, not the type of thing you want to make the newspapers for, but we did. We were actually disconnected from the internet for 2 weeks. So, you know, we've got some past exposure to very sophisticated cyber adversaries. In 2014, you may remember Heartbleed. And when this vulnerability was exploited, an adversary potentially had access to memory, which in this particular instance, if it was a VPN concentrator, they would have access to the session cookies. They could steal the session cookie and take over the user's session. I did want to mention all these slides are available for you. So there's a link there at the bottom. Mandiant actually wrote an article based on that specific exact attack. So after 2014, I kind of redefined what defensive cyber operations looked like at the lab. I put this construct together. We were really going to base cyber operations on researching adversaries' tradecraft, emulating what they do in our environment so we know what it looks like in our environment. You know, there was a data engineering, make sure we had the right data pipelines in place, and then actually doing analysis. It's a great chart, but it doesn't take care of itself. There was some changes we had to make. One is philosophy. We had to approach things different. Instead of focusing on, you know, looking for IOCs and trying to mitigate attacks, we were moving more towards pure data analysis. The other component is we actually built a very strong relationship with our peers, and so much that when some of our peers had incidents, they would call for our assistance. So we got a lot of exposure. Threat emulation is very important, but actually working in an actual incident when there's an adversary at the other end is very valuable. So that was kind of a unique experience we had. IOCs, we kind of moved away from the, you know, we didn't see the value in atomic IOCs. We got more into the behavioral analysis component of it. And then the last very important part of it is failure. And not just accepting failure, but actually expecting some kind of failure. Because if the analysts aren't failing at some level, it means that they're not pushing themselves past, you know, their boundaries far enough. And so this is accepted with the team, you know, the CIO expects it from me as well. So Python and our data analysis challenges. So this isn't a real actual query, but it's just a representation of what our queries start to look like after years of doing analysis. Really, what I'm trying to represent here is what I call the silver bullet query, right? Is like, I'm going to start joining all this data, and I'm going to need to create a query that I'm going to find the compromised host on our network. And what happens is a lot of times is that the queries get too complex, they time out, or we end up getting way too many rows back than we could do anything with. I mean, how am I going to pivot off 50 systems? How am I going to pivot off a couple hundred systems? And I'm going to get into the actual examples of how we're going to iterate through multiple results. You also may have data in different locations, SQL Server, the cloud, maybe your EDR, you just get alerts. Maybe you want to query that database to get data back from it. But ultimately, what I find is that we end up with hitting this analysis dead end, right? You're like, this is what Splunk can do, this is what ELK can do, and then you accept that. So our ability to do data analysis kind of is limited to what our SIM tools, our query languages allow us to do, and it really kind of impacts our ability to do better data analysis. So one of the things I did is I took a few steps back and I said, okay, let's take cyber out of the equation. And let's take IT out of the equation. What are other areas, business areas, doing for data analysis? What I found, there's a lot of tools that people are using, but Python is one of the common tools. And not only just Python, but a lot of the libraries that are built in Python, like Matplotlib, Pandas. I'm going to be showing some examples of how we're using Pandas and scikit-learn, Jupyter Notebooks. And people are using them because of their flexibility and their power. There's a lot of libraries. I just mentioned a few of them. I mentioned about iterating through multiple rows. We're going to go through some examples of some of the data manipulation techniques. There's statistical analysis and machine learning. And just for a disclaimer, Matt or myself don't have a background in data science or machine learning. We are cyber analysts that are looking for a way to get out of that box that Splunk and ELK and the other SIMs have painted us in, right? And how are we going to do that? And we're going to do that with these tools. Now, this isn't a machine learning easy button or a data analysis easy button. This is, hey, I'm at this analysis dead end. What else can I do?
Yeah, so to kind of show this new process and how it can help and benefit us for hunting work, I wanted to walk through some work I did a couple months back where I decided I wanted to implement my own machine learning URL classifier. And we'll basically walk through what that entailed, how I made it, and then once you have these models, what can you do with it? So at a high level view, my strategy or the steps that I took here are such. Starting out, you need data. That's kind of the first step for a lot of the problems in our field. But I actually decided early on that I wanted to, for my classifier, I wanted to deal with a supervised machine learning models. So then I had the additional criteria that I needed a tagged data set. And I'll talk a little bit on the next slide about what that actually means. After that, once we have our tagged data, then we need to do the very important step of designing and figuring out what features we can pull from this. These features are very important because those are what we end up feeding our machine learning model that we're going to end up picking from in terms of the many that are available from the supervised machine learning set. Once we've built our model, how can you measure it? How do you know that this model is good? Is it performing the way you want for your specific use case and needs? And if it's not, what can you do to fine-tune that? And then finally, once we have that model, what then? How do you take that next step and operationalize it? So starting off with the creation of a tagged data set, what the tagged data set means is we need data such as if we're talking about a URL classifier, we need a bunch of URLs. And the labels, or as I'll most likely refer to it later, is target features. So for this classifier, I kept it kind of simple. My classification is a binary. Is it malicious? Is it benign? You could, expand this out if the data allows, and have the classification be, a part in the attack chain, maybe attributed to some malware families or actor sets. But we'll keep it just benign and malicious for now. And while you're pulling together this list of URLs, you do also want to take care and try and balance your target feature as much as possible. You want as many good as bad URLs here, and that's going to help your model learn better. There are tricks to do if your data is unbalanced, but it's simple. It's easier to deal with if it's balanced. And once we have this data and these classifications pulled together, the next step is we need to get it into a format that that the Python modules for scikit-learn, for all the models, can understand. And that usually involves putting it into a pandas data frame. And if you're not familiar with pandas, just think of a data frame as like a glorified table implementation. So once we have our data, we have the next step of designing our features and figuring out what we can actually pull from them. Features you can just think of as like a meaningful observation of the data. I have an example URL here that I'm going to use to kind of walk through a couple different features you could pull from it. So from this example URL, if you look at it, there's a couple different there's a lot of things you can try and observe and try and pull out from it. But one of the things you might notice is this WP content string. That's a good indicator. We can make an assumption here that this is most likely a WordPress website. Another feature, maybe we want to count the number of segments in our URL's path. So, we look at the URL's path, we count the number of slashes, and we have a number. Another thing we could do, as simple as just saying, what is the length of the path in the URL? So these are all features that we can start to pull out. You notice I am going to try and keep a lot of these features numerical. Once more, it's just a way to keep things easier if everything is a number instead of categorical features. And then as you're going through this process, you're probably going to get to the point where you're going to ask yourself, is this feature any good? Is it meaningful? And so one thing you can do at this stage in the process is you can use some built-in pandas functionality for getting correlations. So you can see what the correlation values are between each feature to feature, but more importantly, how each feature correlates with our target feature, that classification. And so what you're looking for is a strong positive or negative correlation. If the correlation value is 0 or near 0, maybe that feature is not good, maybe not a good candidate to include in this process. So while me and Anthony are presenting, we're going to definitely share a good number of screenshots and code snippets, because we want to kind of provide a resource for people after this presentation to come back to and look through. So the expectation is not to understand all the code right away, but I will just point out 3 elements in this code snippet. So this is what a process or feature extraction could look like, and these circled elements here are basically the same as those features we just discussed in the last slide. And so this is what a feature extraction could look like. So now that we have our features, now we need to figure out which model we want to use. And while this is an important choice, it's also one I wouldn't worry about or dwell on too much, as the decision of the model is actually really easy to go back and swap out for a different model if you've got to this point already. Whenever I was first going through this process, I actually started with the k-nearest neighbor model solely because I was following a tutorial, and that's what they were doing. So I followed that tutorial through, and then once I was done, I went back, ripped out the implementation and set up for the k-nearest neighbor, and I put in like a decision tree and then a random forest, and then I was able to start doing some comparisons between these models and seeing, if they do work better or worse for my use case. So as we're creating this model, we do need to return back to the data real quick, all those features we just talked about extracting, because we need to break that data set into two. We need a training data set, we need a testing or validation data set. Rule of thumb is, you have more data in your training than you have in your testing. I just advertise an 80-20 split here. I also call out specifically a couple of variable names here because those are going to be represented in the next couple of slides. So this X-train, Y-train, X-test, Y-test. The X's are basically mapping to those features we just talked about extracting, and then the Y maps to the classification, that benign or malicious. And these two are basically similarly indexed so that they're connected in that way. So in terms of creating your model, here's one way you can do such. I do have an implementation once more of setting up a k-nearest neighbor. I am doing a little something extra here that I wanted to share, and that is I'm using a tool called Grid Search CV. So this tool is nice because when you're trying out these new models and using them for the first time, they have these things called hyperparameters, which are basically the levers that you can influence the behavior, the learning, the performance of these models. And when you first look at some of these models, it's not immediately obvious in some cases the nuance of manipulating these hyperparameters. So there's tools like Grid Search CV out there that allow you to kind of automate away the decision making by basically providing it a ton of different options. And what it will do is it will actually run through every permutation of these options, and then it will tell you which one is the most optimal performing. Now there's obviously, because this is an exhaustive check, there is a performance overhead. It's kind of one of those things you run, go get lunch, and come back and see what the results were. But in this slide, I'm showing off, setting up a couple of the parameters with the ranges of values and the list of options that I wanted to check. On line 10, towards the middle, I actually show, pulling the best parameters that it found out and building a new KNN model from that. And then on my last line, I'm just basically printing out all the relevant information in terms of printing out, what the best parameters that the grid search found, and then how well this model performed on my training and then my testing data. So evaluating a model is kind of a big, there's a lot of ways you can approach it. One thing, because I'm a visual person, that I found to be pretty useful whenever I got to this stage was to use something called a confusion matrix. So here's just a quick little snippet of code, all you need in order to build one. You basically provide it your model, so that best KNN that we talked about in the last slide, and then our training and our testing data. And if you run this code, you'll get something that looks like this. So you have a very simple matrix. This one's a 2x2. Where on the Y, you have your true classes. On the X, you have your predicted classes. So you have your true positive, true negative, false positive, false negatives. And this is really cool because it kind of gives a very easy to understand view of how your model can perform in regards to these different outputs. And it's important because depending on your use of the model, maybe you want to prioritize decreasing one of these quadrants more than the other. For example, on our team, we always joke that we're very false positive accepting, but it's the false negatives that we really want to try and decrease the number of as much as possible. So we don't want that URL to get classified as benign when it was really malicious. So going back, when we were messing with those hyperparameters, maybe you could manipulate those and see how it impacts these quadrants so that you can try and drive your model to perform in a certain way. Another thing, you can definitely return back to your feature decisions you made. There might be cases where you want to drop features, add new features, just to see how they impact and influence the model's performance. In some cases, if you're using, for example, a tree-based model, that model actually exposes some importance values. So the model itself will tell you what it thinks in terms of how useful that feature is. So this is just a quick little plot of those importance values. And essentially, you would see this plot and you would look at which features, were well performing, as far away from zero as possible. And if they are zero or near zero, once more, that's maybe a good candidate for removal from your model. Okay, so now we have a model that's performing the way we want. What do we do with this? So at its core, what we've built so far is something where if we have a list or set of URLs, we can pass it to this model and ask the model to make predictions on what it thinks those classifications are for it. So essentially, we built an enrichment step. So how do we actually use that on our team in order to influence and assist hunt efforts? So to take a step back, a lot of our hunt stuff that we do on the team is centered around this notion of buckets of data, of detections of filtered data. And these buckets, are distilled forms from some of our larger data sets that have been made a little bit smaller, a little bit easier to manipulate and work with as we're building detections or doing these hunt efforts. And these buckets can exist in multiple different ways, or in multiple different sources, such as a Splunk. It can exist in a database, basically anything. And so if these buckets have URLs in it, what we can do is we can pass that to that URL classifier we just built, and then we can take the output from that URL classifier and put it in another bucket. And we could even break apart the output so that the benigns go in one bucket and the malicious go in another bucket. And really, we can build like this whole process if we want. And the nice thing is this process is all automated once you set it up. So there's really little in terms of analyst overhead that you have. Another nice thing is this is a very simple one-step process right now. But really, this could be as complex as you want. You could create a whole chain of steps here where you're doing all sorts of filtering logic, any checks you wanted to do. Maybe you want to even apply multiple machine learning models as part of some pipeline of analysis. It's really as flexible and as powerful as you want to make it. And so this slide, I basically just show off what that one-step process could look like. I have a little bit of code here where I'm just setting up a quick Splunk implementation, running the query over the past day. Then we can pass that output from this bucket of data into our classifier. And then maybe we want to output from this into like a SQL table. So this is just a quick little implementation of SQL Alchemy to use some built-ins to write this table out. And the important parts here are the connecting bits. So this is where you would break it apart if you wanted to make that complicated chain of analysis, if you wanted to go that way.
Great, Matt. So I'm going to take a little different approach to this. I'm going to talk a little bit about command and control. I'm going to make some assumptions here. There's a lot of different types of command and control. There's C3, there's C2 over DNS, there's SMTP. So specifically, we're going to talk about C2 on proxied web traffic. One of the assumptions is that we're doing some type of interception with that. So we're actually got the HTTP headers for our analysis. There's a few other assumptions. We're going to consider that it's low prevalence in our environment, that there's not thousands of people going to this particular domain. This is some domain that a very sophisticated adversary has been waiting to use. We're going to focus on newer C2. So we're looking to try to find this within the first 24 hours being used in our network. And by doing this, I'm going to talk a little bit about different types of command and control activity, and very specifically, I'm going to talk about the beacon periodicity and time analysis. So beacon traffic, there's a lot of different ways, or command and control traffic, there's a lot of different ways you could break this down. But for this talk, I'm going to break it down into three components. One is victim to adversary. So the victim wants something, or the adversary wants something off the victim system. It could be Kerberos tickets, it could be sensitive data. So when we see this, we see like this higher bytes out part, within web traffic. Then there's adversary to victim. Maybe the adversary is loading something into memory on that victim system. And when we see this, we usually see a larger bytes in within our web traffic. And then there's the beacon activity itself. And this, depending on how jitter is configured, they'll have different variabilities, right? But for right now, we're going to focus, because there's not as much victim to adversary or adversary to victim, we're going to focus on the beacon traffic and see if we can identify beacons. The way we're going to do that, our strategy is try to find unique domains like I had mentioned earlier, see if we can filter that down by checking prevalence. Then we're going to do a count and time analysis on it. And if we can get that number low enough, what we want to do is we're going to capture all data for those remaining hosts. Once we do that, we're going to apply some statistical analysis to it, and then we're going to run some k-means unsupervised machine learning on that to see if we can see any relationships between bytes in and bytes out for the hosts that we have. So the first example, we're going to start, and whatever makes sense for someone's domain. I got 90 days here. I'm going back in time. It could be 180 days. It could be 60 days, whatever makes sense. So I'm going back in time, and I'm looking at the first time we saw a domain. And then what I'm doing, I'm saying the relative time is a day or greater. That means that in the last, X days, in this example, in the last 90 days, I want a list of hosts, whether it's domains or FQDNs, whatever it might be. I want to see things that are new in our environment, okay? And after I do that, I get over 7,500 rows. Well, not much I can actually pivot on, right? Well, not in Splunk and not in Elk, those type of tools we can't pivot. But when we're in Python, we can put it in a list that we can iterate through. So then I can just have a for loop and pass that list, that filter.df list, and then format it in a way in that domain query variable that I can pass to that query. And then I can do that in this one. We have batches of 10. So I just do batches of 10 and iterate through the entire list. So then once I've done that, what I can do is I can put them in a temporary data frame, that chunk data frame there, and from there I can actually concatenate them into another data frame. And in this particular example, I aggregated the host column. So with pandas, I have the explode function that I could actually expand that out. So we moved from 7,500 rows to 7,800 rows. I was supposed to be going down, but what happened was that when I did this query, I went back 2 weeks. In the first query, I only went back 1 day, so we got additional hosts. So the actual domain count went down, but the amount of results increased. So then we're going to use this explode.df to then, in another for loop in Python, to pass the parameters, the fields, in a way that we can pass through a variable to the query. And then we're going to do the same thing with chunking that data through. And then, so in this particular example, what the query is doing here is we're doing a time difference. It's looking from the first event to the last event, and it's subtracting that, and then we're specifying it here on what we want that time to be. Do you want it 1 hour? Do you want it 2 hours? Like, how long do you think this has been on your network? And that's basically what that is. And then, so this is beacon activity. We expect that this is kind of like a keep alive, a checking in, so there's going to be regular activity. So what does that count? You can cast a wide net. You can be very surgical, and maybe you studied some adversary or their malware, and you have an idea of what their beaconing looks like. So you can pass that here in these where I have the question marks at. Again, we're going to chunk all that data, we're going to concatenate it together, and then what we do here, we can pass that along again in another variable to then collect all the data, all the web traffic, like we said we were. And in this particular example, we went from 7,500 to 7,800, and now we're down to 38 rows of that source host and the FQDN. So we've actually finally filtered down a little bit. So we did the unique domains, we did the check prevalence, we did the check count in time, and now we've got all web data for those 38 hosts, and that's about 321,000 rows, and that's fine, because next we're going to do some statistical analysis on that. But this is one of the ways that we iterate through asking simple questions, getting results that you wouldn't normally be able, right, to pivot on, and then to actually pass it through in batches and let Python do all the work. So if we think back to that original slide that I had, where I had command and control broken up into three components: adversary to victim, victim to adversary, and then beacon. What we want to do is, now outliers are normally unusual values, as the quote says here, but we know what those values are. It's at bytes in, heavy bytes in, and heavy bytes out. What we want to try to do is focus in on the beacon traffic and try to remove those. There's several methods here. What I'm going to specifically talk about and show an example of is the interquartile range, but you could use z-score, you could use quantiles, percentages. I like the IQR just because it deals with the top 25%, removes the top 25% and the lowest 25%, and then you have that middle 50% of data. And what we're hoping is that's going to be that beacon traffic. So again, this is how I would apply it. I would define my lower bounds and upper bounds for both bytes in and bytes out. And then what I have here, so before IQR, the number range is from 800 to 1400 for this particular host I'm using as an example. So we have 600 to 1400. So we have an 800 byte spread between that data. And then after we applied the IQR at 740 to 880, so we've reduced the spread significantly. And we do that for all of our host pairs, the host and domain pairs. So the hope is now that we've actually removed those outliers. So the next thing, so we think we have our beacon traffic. The next one gets a little tricky. What we're going to do is we're going to group the host and the desk host together and then put them in 1 hour buckets. And then we're going to count those buckets. And I got question marks there because, this is hunting, right? I don't have the number that's going to find the beacon, right? I mean, this is part of an iterative process. Experiment as you want as cyber hunters. But you're going to want to count how many beacons do you expect to be in that 1 hour bucket? Is it 5? Is it 100? Is it 1,000? Your experience will help dictate what that number is. We're going to group them again. And then we're going to count how many buckets didn't meet the criteria, because at this point we don't have confidence that that's actually beacon activity. So what it looks like essentially from a graphical perspective, if I kind of step through this, I look, hey, there's an hour, it doesn't meet the criteria for beacons, that's fine, we're going to count it, right? Do we do the analysis basically on another system? There's like, hey, we got like 3 hours here where it didn't meet beacon criteria. I don't have confidence that this is actually beacon activity. So I won't include that host. And what I do is actually create a filter out filter to filter those hosts out from the original data frame. So one option at this point is I can pivot to our EDR, and I can say there's that domain, and then there's that the host that's going out to that domain. I can pull the process names for those connections, And look right here, I got 27 hosts. If I do that, I kind of filter out the common browsers, we're down to 3 hosts. So maybe that's, and we have Matt Dooley's system here in the middle there. So that's an option. The other, so just to do a check-in to see where we're at, we started with unique domains, we checked prevalence, we checked count and time, we captured all the web data, we did the statistical analysis, and now we're ready to do the machine learning part of it, but what data are we sending to it? The data we're sending to it is the original data frame that we pulled all the web traffic from, using that statistical analysis at IQR component to filter those hosts out that we don't feel confident that they actually had beacon traffic, and then we have a new data frame. But the data frame has all the data, not just the IQR data. So the next thing, we're going to move on to k-means clustering, and to do so, we need to understand what is the optimal amount of clusters, and we're going to apply the elbow method to this analysis, but there's not much of an elbow here. You really want more of a 90-degree or closer to that, and I'm not really sure what I feel the elbow is here. Maybe 6 or 7 clusters might be sufficient, so I'll try the silhouette score, and again, it's really not clear, maybe in the 8 to 10 clusters realm. And then I think back, and sometimes it's not so much of the model performance and the optimal amount of clusters is what you're trying to do with the analysis. If I go back to a previous slide, remember this, and I really wanted to see if there's a relationship between heavy bytes out, heavy bytes in, and the actual beacon activity, and will k-means clustering pull these into those clusters? So you may notice on this slide a little bit of code here. At the top red circle, it has the in clusters set to 4, and you may ask, well, I thought there was 3 areas, right? Heavy bytes in, heavy bytes out in clusters. Well, so I've been messing with this, so I've been working with this, experimenting, for the last 1.5 to 2 years. And what I found is what can throw off the clustering is when I have an extreme value, like someone just downloaded something very heavy and I got like a 1 row line, and it'll throw off the other clusters. So if I have if I add another cluster, and you could argue, I've tried 5, 4 is like my magic number personally. But what happens, it usually catches that extreme value and then pulls the other clusters in appropriately. And that's basically what it's done here. So we see Matt's system there at the top. So we have the beacon, the victim to adversary, and adversary to victim. And what I find very consistently as we do threat emulation is that when the adversary is active, doing things on the system, and it's not just beaconing, that they will fall into 3 different clusters. And this is the data from this emulation exercise that we just recently did, and what put Matt into 3 different clusters. Now this particularly is doing SPN scanning and curve roasting from that system. It generated enough activity to put Matt's system into 3 different clusters. I did want to talk about one other thing real quick, and that is the modularity within these. So Matt went through his models, and that was great. The thing that's really cool here is that it's real easy to take Matt's model and to insert my step 3 or my step 4 and then continue with the analysis. Working in Jupyter notebooks and sharing notebooks, we can do this very, very easily, and we do regularly. But this has been extremely valuable as well.
Yeah, so as Anthony mentioned earlier on, neither of us are data scientists background. We've had to do a lot of learning over the past year or 2. So we did want to dedicate one slide just to the resources we found useful during this. This is by no means exhaustive, but it's a good place to start if you wanted to go down this process.
I will say, in addition, that a lot of these resources that we've used, some of them have communities. Like I know Coding Nomads have a community. I think Kaggle does. I mean, we work at a research lab, so we have a lot of resources that maybe a lot of people don't have access to. So being a part of some of these communities can be extremely valuable. Especially if you need to keep yourself honest. Hey, I always use the example that where my data scientist said, hey, Anthony, port number is a number, right? But it's not a numerical feature. It's actually a categorical feature. But most of these resources aren't cyber related, right? They're going to be heavy business analysis, marketing, trends, things like that. So you got to start thinking about how you apply this to cybersecurity. I know SANS has a class. There's some other vendors that have some classes. There's a lot of university affiliated like boot camps, but again, they're very business focused and general machine learning. And it's really up to you. A lot of what we're doing is just kind of showing you a process and what's possible and kind of what we're doing with it. And how do I apply this? I don't wait for trying to put together the perfect strategy or finding the perfect, class or whatever. Just get started. Put a strategy together, adjust, as your path changes, and execute that strategy. Just start. I always tell people, because you can start, you can change your course, but you can't get the last 6 months you didn't do anything. And that's what we found. We just started, and we've made a lot of progress. In the first 3 months, you guys probably have access to data. Pull data using Python. Create a pandas data frame. Do some searching, manipulate it. And then within 6 months, understand the fundamentals of some of these machine learning models. Some of them are straightforward. Some of them are more challenging. And put together, think about a machine learning challenge that you can actually accomplish, and then execute on that. And that's all we had. Questions?
I guess I'm first. Good morning, and thank you for the talk. So shifting right from after your analysis using Python and pandas, can you talk to us a little bit about furthering your automation with maybe mitigation? Have you perhaps used any sort of orchestration technologies either in your management plane or at your edge devices?
Yeah, so without naming names, we do have a SOAR product, and it does have the ability to run Python in some specialized Docker instances, and you can automate things and put them in these playbooks and whatnot. We've started playing around a little bit with that. We're still kind of getting comfortable and trusting of these new models and how high or low of a fidelity their outputs are. But we are starting to investigate how we can plug that into these SOAR products, yes.
Yeah, the other thing I want to mention too is that in some of these, with some of these models that we're using, even with our SOAR product, it could be a question. This could be a way to ask it a question. Hey, I'm investigating something. Hey, does this look like Beacon? Does it have any kind of Beacon activity in it? And then run that from the SOAR product. It could be an option that the analysts actually run. And then just have this, embedded in the back end.
Good question. Any other questions? Okay.
Great.
Well, if you want to hit us up after this talk, we'll be around the conference all week, so don't feel, just come up and ask us a question. We're happy to talk about it.
Thank you.
Thank you.